Okay, let's dive into this. Welcome to the Explainer, everyone. Today, we're basically putting on our detective hats to solve a very specific but incredibly common robotics mystery. We're digging into Grade 7 Robotics Unit 4 Remote Control and Coordination. We're going to be investigating those unseen forces that allow a human and a robot to communicate flawlessly. Or, as is pretty often the case, the hidden reasons why they sometimes completely fail to communicate at all. Get ready because the true culprit here is almost never what you think it is.
So picture this scenario. You've got the controller in your hand, you're looking right at your robot, you firmly press the go forward button on the remote, and the robot does absolutely nothing. It just sits there like a very expensive paperweight. I mean, why? This super frustrating moment points us directly to the essential question of our whole unit. How can humans and robots coordinate through controls? See, coordination requires perfect timing and perfect listening. But when that coordination breaks down, we as human operators tend to jump to some very specific conclusions.
Section 1. The broken robot myth. Let's look at what we usually blame.
Whenever a robot acts laggy or just totally unresponsive, literally everyone immediately points their finger at a prime suspect. The common myth is that the failure is physical. Our immediate thought is, oh, the motors must be bad, or the batteries are completely dead, or hey, the remote is broken. We always blame the hardware. But the reality is actually quite different. While physical hardware definitely can fail, the true culprit for poor reliability is usually a broken program flow. It's just bad code structure. The robot might have plenty of battery, and its motors could be in perfect condition, but the invisible instructions telling it how to listen to you, those are deeply flawed.
Section 2. Meet program flow. This is the hidden engine of reliability. To really figure out why a perfectly healthy robot is just ignoring your controller, we need to understand the software driving it. So here's our working definition of program flow. It's the structured order in which a robot reads and executes its coded instructions. Notice the emphasis on the word order. A robot reads code line by line, from top to bottom, but to keep a robot running continuously, we use loops to repeat those actions. This program flow is the vital, totally invisible link that maps your manual controls to the actual robot behavior. If the flow is structured well, the coordination is seamless. But if the flow is structured poorly, well, you get a robot that seemingly has a mind of its own. Now, right inside that flow, we have conditionals. These are the if-then checks within the code that actually listen for new user inputs or events. Think of a conditional kind of like checking your phone for an important text message. If I get a text message from my friend, then I'll text back. If your robot's code doesn't have a conditional properly placed in its loop to say, if the human presses the button, then drive forward, the robot simply isn't listening for the event. It is completely blind to your controller inputs. Section 3. Tale of two loops. Time to examine the scene of the crime. And this brilliantly illustrates exactly how this communication breakdown happens in the real world. Let's look at some evidence, starting with loop A. This is the good code. As the loop circles around and around, repeating the program flow, it hits a conditional check for new input on every single pass. It's constantly asking, did you press a button? Did you press a button? Did you press a button? And because it checks constantly, the event handling is spot on. The usability is super high. But then we have loop B, the bad code. This loop checks for input only once at the very start of the program. After that one check, it gets trapped in a cycle of moving or waiting, and it completely skips over the part where it listens to the human. Let's break down exactly how this builds into a total coordination failure. In step 1, you turn the robot on, and loop B fires up. It checks for a controller input once, but you haven't pressed anything yet, so the robot moves on. Step 2, a few seconds later, you, the human, finally press the button. You want the robot to move. But in step 3, the robot misses the command entirely. Why? Because the program flow has already moved way past the conditional. It's trapped in a loop that doesn't include that if-then question anymore. The robot is literally no longer listening. This right here is how poor structure drops commands, even if absolutely every wire and motor is perfectly fine.
Section 4. Spotting the evidence. How to actually diagnose bad code.
So now that we know the mechanics of the crime, how do we spot it in the real world? Well, when you're out there performance testing your manual controls, you need to look for these specific physical symptoms. First up, missed button presses, exactly like we just discussed. You press a button, absolutely nothing happens. Second, delayed turns or lagging movements. Say you press left, but the robot doesn't actually turn until 2 seconds later. That usually means the conditional is inside a loop, but the loop is taking way too long to circle back around to the check. And third, repeated or stuck commands. The robot just keeps driving forward even though you let go of the button. Guys, these are not signs of a dead battery. These are the classic telltale symptoms of flawed code structure.
So the absolutely crucial point here is this equation. A missed command equals evidence of a missing conditional check. When you're assessing a robot's reliability, you have to translate the physical behavior of the machine back into the structure of its programming. If a human and a robot are failing to coordinate, you have to look for exactly where the robot stopped asking for feedback.
Section 5, your diagnosis challenge. Time to apply what you've learned.
Let's wrap up with a scenario for you to figure out. Imagine you're operating an automated robot arm. Occasionally, when you hit the release button on your remote, the arm drops the object too early or maybe too late, or sometimes it just ignores you and drops it at random. What specific evidence would you look for during a performance test to diagnose whether the physical hardware grip is broken or if the program flow just has a poorly placed conditional? How would you actually prove it? Discuss this with your classmates. And just remember, the hardware is only the muscle. The program flow is the brain. Thanks so much for joining this explainer, and happy investigating.